And yeah, that's pretty much it. I will give it over. So today is different. We have one big talk, but we have 3 speakers, which is super exciting. There are 3 people that will actually work together in the same lab, but I will let them introduce themselves with their talk, Physics But Cooler, Taming Quantum Mechanics with Lasers and Ultracold Atoms.
Yeah, thanks, Uze, and thank you all for coming here. My name is Jessie. I'm a graduate student in the physics department here at Harvard, and together with me here are Will and Lewis, and we all work in the same lab. And today we're really excited to share with you some of the science that goes on in the lab we work on and how we think it could be relevant to everyone's daily lives. But before we begin, I'll first let Will and Lewis introduce themselves, just so that you guys see their faces.
Hello, everyone. I'm Will. I'm a postdoc in the chemistry department at Harvard. And prior to that, I did my PhD at University of Colorado.
And I'm Lewis. I'm a third-year PhD student in the physics department and working in the new lab with Jessie and Will.
Yeah, so as I mentioned, so we all work in the same lab. And today we want to share with you what we think is probably the coolest kind of physics. And in particular, we want to tell you how we can tame quantum mechanics with lasers and ultracold atoms. Now, if this title doesn't make sense to you, don't worry. We'll explain it, and hopefully by the end, you'll understand what we're talking about. So just to give a brief overview of what you'll see today. So we'll be venturing out into the quantum world today. And we'll begin by giving a little introduction to the quantum world, where we'll talk about atoms and quantum mechanics and how temperature plays a role in all of this. And then Will tell you about how we can control the quantum world using lasers to make what are known as ultracold atoms and trap atoms like we could with a tweezer. And finally, Lewis will tell you what we can do in the quantum world with what are known as quantum simulators and quantum computers. So I'll begin with a brief, quick introduction to the quantum world. And the main, our adventure really starts with the story of atoms. And so this will really form the backbone for a lot of what Will and Lewis will be telling you about of all the exciting stuff. So I hope you first sit tight and like the exciting part will come. So what are atoms? Atoms are the basic building block of all matter. So if you were to take an aluminum foil from your kitchen, tear a piece out, tear it again, tear it until you couldn't tear it anymore, what you would find are these little building blocks that pile on top of each other and form what is known as this aluminum foil. And to give a sense of scale, so each of these are about a millionth of a hair width, so that's really, really, really tiny, all stacking up to give you your aluminum foil. So this was kind of the picture that scientists had since the ancient Greeks up until about the late 1800s. And in fact, the word atoms comes from ancient Greek. The scientists weren't really content with this picture of atoms. They really wanted to know exactly what went on in these atoms. So later in the early 1900s, they came up with this picture where atoms, if you were to peer further down into these atoms, each atom consists of what is known as a nucleus and an electron that sort of just whizzes around this nucleus. But exactly how these electrons behaved around this nucleus was still somewhat of a mystery. And so scientists wanted to learn more about exactly what was going on. And the way they did this was to use light. So why light? So what is light? If we were to take a flashlight, shine some light, and if we were to send that through a glass prism, so that's just a piece of glass shaped into a triangular shape, and look at what comes out. Typically, you would find the rainbow. So you would see all the colors from red to violet. Now, scientists can use a similar method to understand atoms. So instead of using this light coming out from a flashlight, you can replace that with light coming out from hydrogen atoms. So these atoms will give off some light. You send that light through the same glass prism and look at what comes out. And when scientists did this, what they found was that instead of the rainbow, what they saw were these distinct colors that almost seemed like they were cut out from the rainbow. So there was red, and then in between all the orange up to green is gone. And then there's some blue coming out and then more darker blue. But these were really discrete colors, as opposed to all the colors of the rainbow you would see. And this was really puzzling to scientists because they were expecting to see a rainbow. So what was going on? It took about a decade or two before physicists proposed this model, which we now call the quantum model of the atom, to explain this. This was put forth by Niels Bohr in 1913 and Ernst Schrödinger in 1926. So what's the idea? The idea is, so in our original picture of the atom, so you have an electron and that's orbiting around this nucleus. In the original picture, if you were to sort of just nudge this electron a little bit, it'll just follow suit and it'll just take on another orbit. You can nudge it a little more. It doesn't really care. It can take on any orbit it wants. But it turns out, though, that that isn't really the case. It turns out that these atoms can only have discrete states. So what that means is that it can take this orbit around this nucleus, but if you were to nudge it a little bit, it would jump to something very far away. And furthermore, when it jumps between these different states, it gives off light. And in particular, each pair of these distinct states would give rise to these discrete colors that you saw on the previous slide. And so this is where quantum mechanics got its name, that it's really just discrete states and giving rise to these discrete colors out of the rainbow. So this model is really interesting. It turns out that these atoms actually give off a lot of cool behavior as well. So we know that with these atoms, we can only measure them in these distinct states. So for now, we'll just call them state A and state B. So we can only measure them in these distinct states. But scientists realized that it would be possible in some cases when they try and measure an atom, what they found is that 50% of the time they would get the atom in state A, and 50% of the time they would get it in state B. It was almost like flipping a coin. And no matter how well they prepared this experiment, it would always be this random choice. It would be 50-50. And so scientists called this a superposition state. And it's this idea that atoms can be in multiple states at the same time, and it doesn't really decide until it's measured. So here we kind of pictorially show it as, it's kind of fuzzy between these two states. So this is what we call a superposition state, and it's really cool already. Now what if we try and put two atoms that are in the superposition state side by side, and that in some way they can talk with each other? What would happen if we try and measure the state now of these atoms? Well, there are two possibilities. So we can either measure the green atom first and then measure the yellow, or we can measure the yellow atom first and then measure the green. So if we look at the first case, so if we measure the green, then measure yellow, then this green atom is in a superposition state. And like I mentioned, it's like a coin toss. So 50% of the time you would get state A, and 50% of the time you would get state B. But a curious thing happened when scientists then measured the yellow atom. What they found was that when they first measured the green atom, they found it to be in state A, then when they measured the yellow atom, it would definitively 100% of the time be in state A. Whereas if they had measured state B for the green atom, 100% of the time, they would find the yellow atom in state B. So it's like, whereas measuring the green atom was still a coin toss, once the green atom decides, the yellow atom sort of just follows suit and has already made a decision. And well, okay, you may say that's just because you're measuring green first and then measure yellow. What if you measure yellow first, then measure green? Well, then your yellow atom becomes your coin toss. So 50% of the time you get state A, and another 50% of the time you get state B. But once the yellow atom has decided, the green atom is already decided as well. So then state A would give state A in green, and state B in yellow would give state B in green. And what was even more weird is that it didn't matter how close these atoms or how far these atoms were. So as long as they've talked with each other at some point in time, you can bring these atoms really far apart, like miles away, even up to a satellite, and they would still exhibit this behavior. It was almost like there was some connection between these atoms. And so physicists called this an entangled state, which is when the measurement of one atom affects the state of another atom. So this is really cool. And you may wonder, like, of all this, like, why don't we see this every day? Like, why couldn't we just take some atoms or molecules out of the air, grab some atoms and show these magic tricks to all our friends? Well, it turns out that these atoms, they're cool, but they're not quite cool enough yet. Meaning that normal atoms and molecules at room temperature are simply too hot. So we need to go cold. And actually we need to go ultra cold. So you may be wondering why does temperature play a part in all of this? Well, to answer that, it helps to understand what we mean by temperature. So if you take your typical hot sunny day versus a frigid winter day in Boston, what makes the difference between a cold day and a hot day? It turns out that it's the gas, atoms, and molecules floating out around us. They're actually constantly moving. They're jiggling about, colliding into each other in this really random and actually quite violent motion. And so what makes the difference is that on a hot day, these molecules and atoms are moving much faster, whereas on a cold day, they're moving slower. Just to give you a sense of some numbers, so on a hot day, they would probably be moving at about 1,050 miles per hour. So that's faster than an airplane. So this is sort of an exaggeration. On a cold day, they're slightly slower, but not that much slower. It's still close to 1,000 miles per hour. So this is really too fast for us to actually grab onto and interrogate these atoms and to actually use their quantum properties. So for that, we really need to go colder. And it helps to introduce a new unit for temperature, as if Fahrenheit and Celsius isn't enough confusion already. But in this temperature unit, 0 Kelvin is, so the unit for temperature is Kelvin. And in this temperature scale, 0 Kelvin is where everything would be at a standstill. And it's what we call absolute zero. So it's the lowest temperature that is theoretically possible. And if we were to, our summer day, that would be around 300 Kelvin, lying somewhere around here. A winter day, while it's really cold for us, isn't actually that much colder. It lies somewhere around here at 265. If you were to go a little, just to give a sense of scale, going hot, boiling water would be somewhere around here. If you wanted to look for cold stuff down here, some things you might be familiar with, for example, dry ice you might see in theaters for like the misty effect, or liquid nitrogen in like science fair demonstrations. These are about around 100 or 200 Kelvin, but these are still really fast, like about 500 miles per hour. That's still about like an airplane. So if you wanted to go even colder, you could go out into outer space. You might think that in outer space, there's not much going on, but actually in outer space, the atoms and molecules around are actually still moving at about 100 miles per hour. That's like the speed of a car, a speeding car. So that's about 3 Kelvin. So that's actually still not cold enough for us to be able to grab onto these atoms and to use them. So where do we need to go? We need to go way down here and zoom up maybe 1,000,000 times. And it's where we call ultra cold temperatures, which is about 1,000,000th of a degree above absolute zero. And in this area, things move at about 1 inch per second. And so we really need to go this slow for the quantum properties of these atoms to show itself. And how we get down to this slow and this cold will be the topic of the next part, which will tell you about. So just to summarize this first, this intro to the quantum world, I've told you about how we can learn about atoms with light, and how in the past century, using light, scientists came to learn that atoms come in discrete states that give rise to these discrete colors in the rainbow. And then there's the concept of superposition and entanglement. So in superposition, the atom can't really decide what state it's in until it's actually measured. And in entanglement, measuring one atom affects the outcome of another atom. And then I told you how we really need to go really, 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 really cold for all these cool properties to actually show up. Yeah, and I'm happy to take any questions for this part.
Awesome. Thank you so much, Jessie. I've already started getting some questions, but please, everyone, feel free to write your questions either in the Zoom chat or the YouTube live chat, but I'll get to the ones that we already have. One of them is, you talked about when the electrons change from one orbit to another. Does that mean they turn into an ion?
So in this case, they are still atoms. So an ion would be if this electron was completely pulled apart from the nucleus. That would be an ion. Over here, it's still just jumping between states of a single atom.
And there's the follow-up to that is, the energy released between those two states, is that ionic energy? Is it similar to the energy released when an atom turns into an ion?
So typically that would be smaller, because you, like the further apart you want to pull it, the more energy you need. Ionizing it, so if you want it to turn into an ion, you would need to pull it completely apart. So you would need a lot of energy for that. Whereas if it's just to give off this light that I was showing you, that's just between, they're still close by to the nucleus. Yeah.
Ah, I see. Okay. Well, if our person has follow-up questions, they should write them. I'll ask the other one. How recent does the connection between the atoms has to be, or is there no limits? This is like the talking to each other for entanglements.
Recent, as in time-wise?
I think it's time-wise. Katrina,
Okay.
Correct me if there's other ideas in there.
Yes, that's actually a really good question. It sort of depends on the system, and I guess, so it depends on the system and also the environment it's living in. So if it's constantly perturbed by things in the environment, then this time could be really short. So like less than a microsecond or a millisecond. And so it's actually a big problem these days to try and make this time much longer, so that we can, make them talk with each other, hold them apart for seconds, hours, and still maintain this entanglement. Yeah, but that time right now is pretty short, like less sub-seconds.
Wow. That's too short. All right, there's actually a question related to that, so I'll ask that first. So you showed us when you measure one atom and then the other, they show the same thing, and that's how you know they're entangled. How do you know this is about entanglement and not about the state of your measuring equipment?
So, state of the measure. That's also a good question. Essentially, because the fact that if you measure the green atom first and you get a state, and then when you measure the yellow one, depending on what you had in the green atom, you get something. But if you reverse this process, it's flipped, right? And so if it were something with the apparatus, it would be, flipping it would change things. Well, would fix that problem. I hope maybe that answers. Yeah, this.
Yeah, thank you. If there's follow-ups, you should feel free to write in the chat. There's another question. How did the hydrogen atoms emit light through the prism? What part of the process nudged the electrons?
That is also a good question. So yeah, it's not as simple as just a finger like touching it. Typically, you would actually first need to excite it there, and then it will just naturally, because the atom wants to be in the lowest energy, so it will naturally want to fall down. So you kind of have to nudge it to go far away, and then it'll naturally want to come back. And so that process gives off the light. And how we nudge it is, we'll actually talk about that in the next part. So how we can make it from this to somewhere a little further for it to come back. Yeah.
That's exciting. All right. Another question, this is from our YouTube audience. Does increased temperature break the entanglement?
Yes. So typically, so that is why we really need to go really, really, really cold. So, and why in our normal, like when we think about the world around us, our normal world around us, we don't think things are entangled. That is because things are just too hot and these lines are very fragile.
All right, thank you. There's a follow-up with regards to the question about the apparatus. I think the previous question might have been whether the apparatus is affected by what is being measured. Would measuring with two different apparatus have the same result?
Yes, so this is completely regardless of the measuring apparatus. Yeah. And people have done experiments where they, no matter what the experimental setup is, this is what they think they should see, and then this is what happens. Yeah.
Awesome.
So that's actually like, if I can just quickly say that is like a subject of continued study kind of thing. Like there have been a bunch of recent big experiments being like, if we design the best apparatus we possibly can we make like 100% sure that this entanglement really does exist? And so far, everything that people have done shows it does really exist.
Yeah. So that's kind of related to like the philosophy of quantum mechanics, getting philosophical. Yeah.
I just got another question. Does warmer temperature actually stop entanglement or just make it too short to be realistic to measure?
I guess it's kind of both, because if you can't measure it, then it's not entangled. But yeah, essentially, you could think of it like it's just too short-lived.
Okay. Yeah. And related to this is distance not a factor at all in entanglement, or is it just because there isn't enough time to measure both when they're far away?
So practically, it is a problem, but so in the case of, but people have done experiments, so not necessarily with atoms, but with other objects. So they can put one on Earth and another on a satellite, and this entanglement still does happen. Yeah.
That's super cool.
But for atoms, it might be more difficult because you need to physically bring an atom somewhere, and that process might lose the entanglement.
And I'll talk about how physicists use light, in particular lasers, to control the motion of atoms, how we make them ultra cold, and something we use in our lab called optical tweezers. So historically, until about the 1980s, physicists were still discovering these properties of atoms, so how the quantum properties of atoms generate their structure and how they generate this discrete spectrum of colors that they emit. And while people are still developing that understanding today, they also have been studying ways to control quantum systems and develop applications for them. So this has been a really exciting field where some of the most interesting advancements in physics have been made. So you may have heard of some of these Nobel Prizes which were awarded to discoveries in the field of atomic physics in the last few decades. So something created in 1989 was cooling atoms with lasers, and that was awarded a Nobel Prize in 1997. In 1995, there was a phenomenon called Bose-Einstein condensation, which is demonstrated. And I'm not really going to talk about this today, but there's a little bit of information in a link on in our handout on this, and that was awarded a Nobel Prize in 2001. In the 1990s, people developed techniques to control individual atoms, and that was awarded a Nobel Prize in 2012. And in the 1980s, in particular in 1986, was developed the technique of optical tweezers, which I will talk about today, and that received a Nobel Prize in 2018. So let's dive in. So the most important thing you need to know when it comes to controlling atoms with light is that light can give atoms a push. So when an atom, say in a higher energy state, as Jessie was talking about earlier, if it emits light going into a lower energy state, then it actually gets a push from emitting this light. Similarly, if an atom in a lower energy state absorbs some light going into a higher energy state, then it also gets a push from this. And physicists use these pushes to control atoms. So in particular, the tool that we use to do this is a laser. And you've probably heard of lasers. So you've probably seen them, for example, laser pointers in classrooms. And they're a special type of light source with some particular properties. So what are these properties that we care about? Well, one property is that they are what we call monochromatic, meaning mono meaning one and chroma meaning color. So they emit just one color of light. So that makes them particularly good for talking to atoms, for giving atoms pushes, because they can emit light just near one of these colors that atoms like to absorb or emit. In addition, the light that lasers emit goes only in one direction, as you've probably noticed, for example, in laser pointers. So one property or effect which you have probably noticed in your everyday life, which is essential to cooling with atoms with lasers, is the Doppler effect. So I'm going to play a sound, which is something you'll be familiar with. And this is a sound you've probably noticed in your everyday life, the sound of a car passing at high speed. So let me know if you can hear this. So what you're going to hear is as a car is coming towards you, you'll hear high pitch. And after it goes past you, the pitch will get lower. So let's listen. Okay, did you all hear that? Yes, okay, great. So you probably noticed initially the pitch is higher and then the pitch is lower. So that I'm depicting in this little video here with these red rings. So this represents the sound coming out of the car. And when these get closer together as the car is coming towards you, that represents the pitch getting higher. And after it's passed, these rings get further apart, representing the pitch being lower. Let's listen one more time. Okay, so atoms, when they're being hit by laser light, experience a similar effect. So an atom that's moving towards the source of light will see the pitch or the color of this laser light get higher. That means for light, that means it looks more blue. And when atoms do this, they feel a force that pushes on them. The pushing force gets larger. And similarly, when they're moving away, the force gets smaller. So we can extend this analogy a little further to describe how we trap and make atoms cold. So here's say if you're a person and you're hearing this vehicle, maybe it's an ambulance coming towards you and you need to get out of the way. Well, you might move away from it to get out of the way. Okay. But there's an ambulance coming from the other direction. You need to move out of the way of that one as well. Okay, so maybe in this picture, you're going to move up. Okay. But oh dear, okay, there's an ambulance coming from the other direction as well. You need to move out of that one, the way of that one as well. You might move down. And of course, you can predict what's going to happen here. If we have, this is a pretty hard scenario to imagine for a person in real life, but this is in fact the scenario that we create for atoms. In that scenario, I'm not sure what you would do. I might be completely trapped, and that is actually what we do for the atoms. So if we have a bunch of atoms in the middle here, maybe inside a glass chamber, what we do is we send lasers at them from the right and from the left, and from the top and from the bottom, and from the back and from the front. And these lasers push on the atoms. So when the atoms are moving towards this laser, they get a push to push them in the opposite direction. And when they're getting these small pushes from every direction, this actually cools them down. In our experiments, we use magnets to sort of take the place of this, this box here. And so the combination of magnets and light, we give a name, and that's called a magneto-optical trap. So if it were not for the pandemic, we would be giving lab tours during Science in the News. So I'll give you a quick little virtual lab tour with some photos. So here's a picture of the inside of our lab. So you can see these three big tables here. The experiment itself is on the table on the left in that black box there. And the other tables are full of lasers. And I'll show you a couple cool photos, which Jessie sent to me a couple hours ago of these lasers inside the lab, just because they look pretty cool. One thing that's nice about this virtual presentation is that we could not do this in real life because these lasers are pretty high power devices, so you need to be very careful around them. But I'll show you them virtually. So here's an orange laser, orange yellow laser that we use for sodium atoms, and here's a red laser that we use for a different purpose, also for sodium atoms, as it turns out. Okay, so that's a little virtual lab tour. Inside the box where we keep the experiment is where we trap and cool these atoms. So let's have a look in there. So here is inside the box. I've drawn a little arrow for scale. So right in the center of this picture, this light colored rectangle that you're seeing, that's a glass vacuum chamber. And right in the center here, inside this circle, you can see a little yellow fuzzy blob. That's actually a cloud of sodium atoms in a magneto-optical trap using that technique which I talked about earlier. And these atoms are actually at a temperature of about 1/1,000,000th of a degree above absolute zero, just as Jessie was talking about in the first part of the talk. So this makes them basically one of the coldest spots in the universe. Oh, and just for another cool little demo, this is looking even closer down a microscope at that cloud of sodium atoms. So in the middle there, this is that little yellow cloud dancing around a little bit. And when it disappears, that's us turning off the lasers. So let's watch again. It's floating there, and maybe it's going to disappear. Let me show. Oh, okay. Well, the video ended. Okay. So that's one way that we trap atoms with lasers. But there are other ways as well. And I'll tell you about a few of those. So one of them is called an optical lattice. And this is a bit like an egg carton made of light. So this orange 3D picture on the left here, this is something like a plot of the amount of light. So the up and down axis, the high points are where there's a lot of light, and the low points are where there isn't very much light. And because the atoms feel pushes from the light, they like to sit like eggs in an egg carton, which I'm showing on the right here. They like to sit in those dips. And they can sit in these dips, but if they have enough energy, they can hop from one dip to the next. So that's one technique called an optical lattice. Another technique, which I alluded to earlier, is called optical tweezers. So in this technique, we use a microscope lens to focus a laser beam down to a very tiny point. The width of that point is something like 1/100th the width of a human hair. And using this laser beam, we can actually trap and grab onto just one atom, and we can move it around. And this is something that we do in our lab. So I'll show you a little, as one final thing, I'll show you a little video of us doing that in the lab. So this video is taken by the microscope next to the glass cell. And so what you're going to see here is, it's a black and white video. So this big fuzzy blob, which you're going to see, is a zoomed in picture of that cloud of sodium atoms. And you'll see a vertical line of 10 dots. And those are 10 optical tweezers, which are grabbing 10 individual atoms and holding them inside the vacuum chamber. So let's watch. Okay, so you can see the cloud dancing around, the sodium cloud dancing around, and you can see these bright spots in the middle. So those are individual sodium atoms. Let's watch this one more time, just for fun. Cool. All right. Oh. I guess we have to wait till the video ends. Okay. Okay, so in summary for this part of the talk, lasers can be used to push atoms. And using the Doppler effect, we can use lasers to cool atoms to millionths of a degree above absolute zero. And we use several different types of optical traps to control atoms in different ways. And I'd be happy to take your questions.
All right. The first one is actually, please type your questions, I'll repeat again, in the Zoom chat or YouTube chat. But we already have one. Why do we use sodium atoms and not other atoms?
Yeah, that's a great question. Sodium is an atom that we like because it turns out these techniques for trapping atoms and cooling them with lasers are easier for some atoms and more difficult for other atoms. And I alluded earlier in the talk to how the rules of quantum mechanics have helped us to understand the colors of light that some atoms like to absorb and emit. And it happens that sodium has only very few colors that it likes to absorb and emit. And it turns out that that makes it easy to cool with lasers, because we don't need very many colors of lasers to control it. So that makes it a convenient atom to use.
Are the lasers, this is kind of related to that, both yours and Jessie's part, but are the laser colors that you use to trap these atoms the same colors that they emit if we did like the hydrogen flashlight that we showed? Are they the same lights?
That's a great question. So I didn't really go into a lot of detail. Of course, I simplified a lot. And it so happens that in the case of the magneto-optical trap, the first type of trap which I talked about, yes, the color is the same. So you may have even seen, you know how street lamps, out on the street, there's yellow light coming from street lamps. Those are sodium lights. They use hot sodium inside those lights. They're giving off that orange color of light. That's the same color which we use in our lasers to push around the sodium atoms. So yes, in the case of the magneto-optical trap, yes. In the case of the other types of traps which I talked about, sometimes no, but I didn't really get into detail about that.
Okay, thank you. There's another question in the chat. How many orbits are possible for sodium atoms? How many different temperatures? Does making them colder mean you're pushing electrons closer to the nucleus?
Great question. Let's see. So, how many orbits are possible? The number of orbits is still very, very large. In fact, technically, as the electron gets further and further away from the nucleus, there are more and more states, and so there's almost an infinite number, but that's sort of a technical detail. What's important is that the number of low energy states is small. So let's see. And does making them colder push the electrons closer to the nucleus? So making them colder means that the individual atoms, so the nucleus plus electron, is flying around more slowly. So the electron could be close to the nucleus or it could be further away, but the whole ball of the nucleus plus the electron is moving around slowly, and that's what it means to be cold.
All right. Another question is, why do you want to isolate each atom? Like after you put them in the egg carton, what do you do with them?
Yeah, that's a great question. So controlling individual atoms makes it much easier to control the entanglement that Jessie was talking about. And in fact, that's going to be important for what Lewis is going to talk about in the next part.
Awesome. Another question is from Pedro. In terms of motional quanta, how cold can you make your atoms? Can you reach the ground states? I assume you're limited by the Doppler limit.
Clearly, we have an expert because there's a lot of language in this question, which is pretty expert level. So we can make, in the optical tweezers, when we're holding single individual atoms, we can make the atoms basically as cold as they're allowed to be by the laws of quantum physics, which does mean the ground state. And actually, that's one reason that we like to use optical tweezers, because it so happens that it's easier to make them as cold as they can get. But that's a bit of a technical detail.
Awesome.
Okay, great. So, hey everyone, again, I'm Lewis. So Jessie and Will in the first two parts of the talk gave you some background on what atoms and sort of basic quantum systems are and how we can control them. And now I'm going to tell you a little bit about why we might want to do that. Specifically, I'm going to talk about two kind of applications of all this ability to control quantum systems that we've developed. And those are quantum simulators and quantum computers. So let's start with quantum simulators. Quantum simulators is basically a word that we use to talk about clever experiments we can do with trapped atoms that will allow us to understand some specific quantum materials better than we currently do. So what's a quantum material? Basically, it's something that is made up of lots and lots of atoms, which has special properties due to the quantum interactions of those atoms. So essentially, it's just a material behaving in a quantum way. To give you a concrete example, I will talk a little bit about superconductors. Superconductors are a special type of metal, essentially, that can conduct electricity really, really well with no resistance. And they can also be used to produce really high magnetic fields. And superconductors rely on quantum interactions within the material. And like our atoms, they actually need to be very, very cold. They're not quite as cold as the atoms for those quantum interactions to be present. Why would we care about superconductors? Well, if you've ever been in or seen an MRI machine, MRI stands for magnetic resonance image, you've actually used a superconductor because these use superconductors to generate the really high magnetic fields that you need to image inside the human body. The trouble with quantum materials is that they are complicated, more complicated than classical materials. And in the case of superconductors, despite the fact that we use them in things like MRI machines, we actually don't really understand how they work very well on a fundamental level. And that's where quantum simulators come in. So first, let me try and explain a little bit about why quantum materials like superconductors are harder to understand than classical materials. Say you have some extremely classical object. How does it behave? How does a classical material behave? Well, say we have some billiard balls. These are large, they're macroscopic, like you can hold them in your hands, and they're usually hot at room temperature. And say we have two of these that start off far apart, and then they collide with one another, like this. And you notice they bounce off each other. So they have interacted in some way. These two billiard balls, they come together, and then they collide, and they'll make a sound if that's happening in real life, and then they'll go off in different directions. But that interaction is very brief. It basically only lasts while they're like right next to each other and touching each other. And then when they're not touching each other, they're essentially independent. And we don't really need to take into account like them talking to each other, which actually makes them kind of easier to simulate and do calculations about. How's that different from a quantum material? Well, now say we do our billiard ball experiment on a microscopic scale with atoms instead of billiard balls. And we have two atoms collide and then move apart. Well, what can happen in this case is, remember Jessie mentioned that if two atoms talk to each other, they can become entangled and start developing links across long distances. And that's exactly what can happen if we have this happen in a material. Two atoms might come and collide with one another, and then once they leave, they still have some entanglement between them. And so they can continue to affect each other at long distances. And if we really want to understand a material made up of interactions like this, we not only need to understand what's happening when they're close together, we need to understand these links that they form as well. And materials don't just have two atoms in them, they have lots. So we can start adding more, and we'll get more and more of these links. And eventually they'll form this kind of spider web of entanglement. Basically with all these sort of different web of connections you can have between all the atoms in your material. So how many connections are we talking about? Say we have like a penny-sized bit of superconductor. Well, how many atoms are there in that? Turns out it's approximately this many. That's 3 with 23 zeros after it. So that's quite a lot of atoms. Okay, well, how many of these different connections? How big is the web that these atoms in a penny-sized superconductor can form? Well, that's approximately this many, which is a much larger number, as you can see. And this is kind of the heart of what makes quantum materials difficult to work with, because there are so many of these connections, and there are actually so many that we can't really do very useful simulations of these kinds of materials, even on our most powerful computers, because there's just too many interactions to keep track of. So that's where quantum simulation comes in. There we want to get a manageable number of atoms, say a few tens or a few hundreds, which we can kind of individually control with lasers. And we then use light to trap them in some particular configuration and control how they interact. One of the most common sorts of traps we use is actually this egg carton shaped trap called an optical lattice that Will mentioned. And it turns out in this sort of trap, we can get atoms to interact with each other in a way that looks a lot like the way they behave in a superconductor. And we can actually study this web of entanglement that is generated, but on a smaller scale, on a more manageable scale. And this is what we call a quantum simulator. It's not literally a superconductor, but it's a sort of toy model that behaves enough like a superconductor that we hope we can study it and learn something about the interactions of the atoms in a real material. Okay. That's quantum simulators. I'm going to change tacks and give you a very brief introduction now to quantum computers. Quantum computing is in the news quite a lot. If you follow any sort of science or mainstream news, you might have seen headlines like this. about quantum breakthroughs at places like Google and IBM, why quantum is going to be here sooner than you think. There's a lot of talk about the quantum revolution. And of course, people are already trying to figure out how to make money off quantum computers. So what is a quantum computer, and how is it different to a normal computer? Well, a normal computer, or a classical computer, which just means a non-quantum computer, essentially, is made up of essentially a series of ones and zeros that are called bits. These bits you can think of as basically like a light switch, or like any electrical switch. You have two states. You can have 0, which corresponds to off. If it was controlling a light bulb, that means like the light bulb is off. Or you can have 1, which corresponds to on. And our computers are just made up of lots and lots of these individual switches. Computer programs, like the ones you're using to watch this talk right now, are essentially just made up of tons of these bits and specific instructions about what to do with them. So as an example of a basic instruction, you could implement an AND instruction between 2 separate bits. So that's basically like asking, okay, we're only going to turn on some light if both of these bits want it to be on. So if both of these are in 1, it's going to be on, otherwise it's going to be off. So in this initial state, you see one of them is in 0 and one of them is in 1. So our answer is going to be 0. It's going to be off. But if we put both of them in 1, well, now the answer is going to be 1, and the light's going to be on. So we've implemented an instruction between these 2 bits to calculate something else. Okay, now how do we make that quantum mechanical? Well, remember the discrete states of atoms that Jessie introduced. You can have some atom in a state A or a state B, which is just determined by where the electron is. Well, what we're actually going to do in a quantum computer is we're going to map that onto zeros and ones. So instead of our electrical switch, we're now using the states of an atom, where A can be 0, and A can be 0, and B can represent 1. So we're now actually kind of encoding information in the atoms themselves. But the neat thing about a quantum system is, like Jessie mentioned, it doesn't have to only be in 0 or 1. It can be in this superposition state, where essentially it hasn't decided if it's going to be a 0 or a 1. And this system where we're using an atom to represent a 0 or a 1 state, we call that a qubit, or a quantum bit. That's literally all it means. It's a quantum bit. So it's a 0 and 1 encoded in some quantum system. So how's that superposition useful when we're trying to make a quantum computer? Well, one of the really important things to know is that we can still do operations. We can apply instructions to the qubit without measuring it and without destroying that superposition. So if we have this AND instruction with now one of the inputs being in a superposition state, in fact, we'll get an output that is also in a superposition state. So now this kind of output hasn't decided if it's going to be in 1 or 0. And it actually won't decide if it's 1 or 0 unless we measure it, or if we measure the input qubit. Kind of in a neat link, actually, this is generating entanglement between the input and the output of your operation. And so here, sort of one of the things that's important is that we basically have both possible answers to this question of, do both these people want the light bulb on at the same time here, right? And we just have to decide which one we really want. So how do we do this property? How do we use this property to do anything useful? Well, we need to give our quantum computer a question to answer. And say we have this question: what 6-digit PIN code will give me access to my money at this bank? And these sort of 9 numbers that you can pick are not super useful for a quantum computer. So let's make a simple PIN pad with just a 0 and a 1, where you have to put in your right sequence of zeros and ones to get your money. So classically, the way you might do this is just to try all the different combinations of 6 zeros and 1s. So you can think, okay, did I leave the passcode at all zeros? Well, no, that might not work. Or is it this? That might not work either. And you can keep going through different combinations and just testing them out until eventually maybe you hit on the correct one. Though by that point you might have been locked out of your credit card. So how could we maybe do this better with a quantum computer? Well, the way a lot of quantum algorithms work is that essentially you start off with, say, a bunch of qubits in superposition states. Like I said, we kind of have lots of different answers here. In the case of sort of the AND instruction, we had 2 possible answers. But actually, if we measured sort of each of these qubits individually, they could each be in either a 0 or 1. So we have the potential to get all of the different possible 6-digit combinations of zeros and ones here. So what we want to do is somehow get from that to the actual correct answer. And so we're going to apply some operation to this set of qubits. And our goal here is kind of to get closer to the right answer. And I'm kind of cheating here with a pin pad example because you couldn't quite do this with a pin pad, because what you need is to be able to somehow ask whether you're closer or further away from the correct answer. So imagine we have a pin pad that will give us a hint, and we can kind of ask it, okay, is this new state of the system closer to the correct answer, closer to you giving me my money? And if it is, then we'll kind of keep going in that direction. And you see I'm sort of graying out some of these numbers more than others. And that's basically because the state of all of these qubits is kind of collapsing onto one correct answer. And eventually what we want is to get a single answer out, which is the correct one. So this is my last slide. The important question, I guess, is that better than a classical computer? And the answer is sometimes. If we are clever about it, the goal is to do that process of converging to the correct answer in a smaller number of steps than it would take to just try every combination. So basically, we're trying to do it in a smaller number of steps than a classical computer could do. And that's not easy. We need to come up with clever ways of basically like asking if we're getting closer. And mathematicians are working on ways of doing that, and also on working on proving that quantum computers can solve some problems better than even the best possible classical computer. Some sort of examples of things a quantum computer could do. One sort of very related one to this problem of getting into your bank account is cracking encrypted data. A lot of things online, like your passwords and sort of credit card details, are actually basically protected by just having to sort of guess really large passwords. And a working quantum computer could potentially crack some of those. There are also, and this kind of field is called cryptography, is like protecting data with passwords and mathematical problems. That's a sort of near-term thing that quantum computers could do, maybe like in 10, 20 years. Don't hold me to that, but that's kind of one of the most achievable goals. There are other sort of more far off and difficult problems that people think that quantum computers might be able to solve, but it's not so certain yet. Stuff like understanding chemical reactions better, or even sort of potentially designing new medicines, sort of new medical treatments with molecules that basically you could only figure out sort of what will work to treat a disease with a quantum computer. So with that, I have explained to you a little bit about what quantum simulators are, and how they can help us understand complicated quantum materials. And I've talked to you about how quantum computers can use superposition and entanglement between qubits to solve real-world problems. And that's it for our talk, where we've walked you through atoms, how to control them, and what we can do with them. And I'm happy to take questions.
Thank you so much, Louis. We already have a few questions, but feel free to write your questions in the chat. This is the last part of our talk. One of them is, you kind of touched upon this already, but what are quantum computers currently used for? Can you give some examples?
That's a very good question. And honestly, currently, they're not used for much, in the sense that they're still in a very early phase where we haven't even really decided what the best method of making a quantum computer is, let alone kind of made the best ones we possibly can. So for example, in all of our computers, we use silicon chips to do classical computing, but that only sort of after some process of people trying out a lot of different ways of making a classical computer, people decided silicon chips were the best way to do it, and then they started making laptops or whatever. So we're kind of in this very early phase of trying out a few different things you could use to make a very basic quantum computer. But some of the things that people are looking at doing with near-term quantum computers are this, understanding chemistry, for example. Basically, you can use quantum computers to do very difficult calculations about what the sort of energy of different molecules are. And that's information that is useful to chemists in order to predict sort of how those molecules might react with one another.
That's super cool. There's a question kind of that relates to that. How far are quantum computers from being operational at all? Not just especially effective.
Yeah, I mean, that's a very, I don't know, you can answer that question in a lot of ways, in the sense that there are quantum computers that are currently working. Even at Harvard, for example, there is a quantum computer with 100 qubits that it can do quantum computations. It just can't do very useful ones yet. So it can't do anything really better than a classical computer. And Google have a quantum computer as well that they sort of say can do one very specific task better than any classical computer, but it's not really a task with any super present applications. So I guess quantum computers are working. We just need to scale them up to get them to do useful things, and that's kind of hard. That's a challenge.
Maybe I could add a little bit that actually these two things we've talked about, quantum simulators and quantum computers, in many ways, I think people think of quantum simulators as being on the way to quantum computers. So the 100 atom quantum system, which Louis is talking about, is a very effective quantum simulator. So that's sort of on the way to a working quantum computer.
All right. Another question about, for qubits, do we intentionally use only 2 orbit states? Could we use more?
That's a really good question, and that's something people are very actively looking at now. Actually, there's another sort of category of quantum systems people call qubits have 4 levels, or there's also people talk about qubits, which have 3 that could encode 0, 1, and 2. So people tend to go with qubits because that's most similar to the way we do classical computing and the way we normally encode information efficiently in computers. But you can definitely potentially use more. It's maybe technically harder. You have to get them under control. Yeah.
Awesome. Another question we have is, which quantum computer platform is most likely to become the most powerful and reach ultimate quantum supremacy? Are there universal quantum computers which can process anything?
The which platform one, I I probably have a conflict of interest answering this question. So in our lab, we're actually kind of trying to develop a new quantum computing platform using actually trapped molecules, which we haven't really talked about, but is sort of the end goal of what we do in our lab. We want to go from these like control of atoms to control of molecules. So I think that one's pretty exciting as a quantum computing platform, but it's in the very early stages.
By platform, do you mean like egg carton versus tweezer, or what do you mean by platform? Can you?
Yeah, I kind of mean partly egg carton versus tweezer. So like the way you trap them and arrange them is one thing, but also literally like the material you use. So we've talked a lot about atoms, and atoms are one way you can represent qubits. You can also actually represent qubits using superconductors, which is what Google does. And that's kind of another whole can of worms. But yeah, there are lots of different ways to make a qubit. I think the superconducting style that Google uses is the most developed, but it's not necessarily the one that I think will win out in the end.
A follow-up says, I've heard ions are the best, but
ions are well known to be good. Yes, they're probably a close second to superconductors. I wouldn't want to not mention ions.
All right. Another question is following up from the previous one. With the laser, do we both push atoms physically and electrons closer to the nucleus, or only the former?
Should I jump in and answer this? That's a great question. And I really simplified a lot in talking about how lasers push on atoms. So I talked about absorption and emission, so atoms absorbing light and emitting it, and how that can give them a push. So when the atom is absorbing light, typically the electron would move further away from the nucleus because you're putting energy into the atom. And then when the electron falls back down closer to the nucleus, as Jessie talked about, it'll emit light. So in that way, the laser does control how far away the electron is from the nucleus. But that because the absorption and emission gives the atoms a push, that can also move the whole atom around. So in a way, the answer is both.
Awesome, thank you. There's another question, but before I ask that, I want to put in our feedback form in the chat. It's both in the Zoom and the YouTube chat. It's a very short feedback form, so if you're heading out the Zoom door, please fill the feedback form so that we can figure out what to do next. All right, this is a more general question, I think, for like all three of you probably. I've heard some people mention that special relativity doesn't explain all of the data that we have. If this is true, what are the holes in it?
Anyone else can feel free to jump in if they want, but I mean, I'll just say, it is true that there are some like inconsistencies between special relativity, which is our sort of and general relativity, which is our current best understanding of how things work at very large scales and how gravity works, for example, and quantum mechanics, which is how sort of things work at this very small scale that we're talking about. And we, physics as a field kind of is still grappling with how to resolve this apparent contradiction. And that's, I guess, one of the like really grand challenges in theoretical and experimental physics, I think, is trying to figure out how to reconcile these different pictures we have of the universe. Because quantum mechanics works really well and we can use it to like control systems at this small scale, but it doesn't quite match with what we see at this very large scale.